going back at precipitation reaction, I would like to talk about more detail of precipitation reactions, and then I go back again to redox reactions. What is the definition of precipitation reaction? It's a reaction which results to the formation of insoluble solid, as you see here. This is PbI2, which is not soluble in water. How do I know it's not soluble in water? I give you a table that you can predict solubility of compounds, and you will use that.
Is there going to be a chart or table with the charges for the polyatomic ions?
Yes.
Okay.
So going back to the same reaction, we reacted sodium iodide to lead iodide. We obtained, lead nitrate. We obtained lead iodide and sodium nitrate. This is a precipitation reaction because of this fact. You have formation of a solid product, insoluble product, from reagents which are water soluble. So guys, that's why the insoluble part is called precipitate. That's why this reaction is precipitation reaction. This is not precipitate, this is water soluble. So formation of insoluble solids shows precipitation reactions. And if I go further, I'm going to break down the meaning of aqueous. What's aqueous? What's aqueous? Which is correct, by the way, aqueous or aqueous? Which one is more familiar to you?
I heard it as aqueous, but...
Aqueous. Yes, okay, good. So guys, go ahead.
What is the 2 NaL? Is that 2 sodiums and oh, it's an iodine.
Yes, sodium iodide, yes. Was it Caleb?
Yeah.
Thank you, Caleb. Okay, that's the fact that this is water soluble. And previously we told you, if you add salt, table salt to water, it's water soluble. Why is it water soluble? What does that mean? It means breakdown to its corresponding ions. If PbNO3 is water soluble, can I say it means in water it breaks down to its corresponding ions? Can I also say the same for sodium iodide? Because from the table of solubility, we can check to see it's water soluble. That means its solubility is because of the fact that it breaks down to its components, break down to its counter ions. And what is the meaning of S here, solid, not soluble? That means this one doesn't dissolve in water because it does not break down to its corresponding ions. So I can't ionize insoluble solids. And then if I look at NaNO3, it is water soluble based on the table of solubility. That means it dissolves in water because it can break down to its counter ions, positive and negative ions. Are you with me so far?
So if it breaks down to its ions, then it's considered water soluble?
Yes. Or it is water soluble based on what? Do you see my screen?
Yeah.
Yes.
Oh, sorry. So if it doesn't change, it doesn't, that means it never broke down.
Right. So
Makes
if I have this equation, guys, if you have an algebraic equation and you have equal terms on both sides, can I cancel them together? Another word, can I cancel 2Na from the right with 2Na from the left?
Yeah.
And there must be 2I hidden under the screen on the right hand side, because this was result of formation of sodium iodide, which had sodium and I. Can I cancel the 2I and 2I? What else do you see which can be cancelled? How about 2NO3 and 2NO3? So what is left over in these two equations? Can I say what is left over is the simple reaction? I couldn't cancel Pb plus 2 because PbI2 never broke down to Pb plus 2. I couldn't cancel I. Never mind about what I said here. No, sorry about that. So I is remaining. So on the left, I have Pb plus 2 and I minus left, and PbI2 is the product of these two ions. And because PbI2 is not water soluble, it doesn't break down to water, so I can't cancel Pb plus 2 from both sides. So guys, this is called net ionic equation. This is what really happened in the test tube, and nothing else changed. It simply means, just a moment, sodium was Na plus 2 before, it remains, 2Na plus, it remains at 2Na plus. Nitrate was 2NO3 minus, it remains as 2NO3 minus, no changes. But Pb plus 2, which was free, and 2I minus, which were free, are now bonded together, and they don't want to separate. They made a solid. They used to be water soluble. So we call this, these are the two ions which reacted together, which changed, nothing else changed. That's why we call this net ionic equation. Go ahead. Go ahead with the question.
Oh, I was just gonna say, so the reason that you were able to cross out the nitrate and the sodium on both sides of the equation is because they're both on either side of the equation, right? Like you would with algebra?
Correct. Exactly just like algebraic equation. Yes.
Okay. Thank you.
You're welcome. So you just learned how to write net ionic equation in a precipitation reaction. A net ionic equation shows real players. I want to give you an example. Suppose you are going to a basketball game. I'm watching the game. Somebody can take a picture from the top of the dome, which will show the players, the real players, and people who are spectators. And then you say, I really want to watch the real players. I don't care about the spectators. The real players, you can separate them, take another picture, zoom on the real players, ignore the spectators, then you have a better understanding of the game. That's what we are doing here. We say the real players in this chemical reaction are Pb plus 2 and I minus. We changed. The other ones, which used to be the same before and after. See, sodium before and sodium after, they are the same. NO3 before and NO3 minus after, they are not the same. They are the same, they are not changing. So because of that, those which are canceled, like sodium ion and O3, we call them spectator ions. So the real change is shown by net ionic equation. The spectators, they just sit and watch, they don't change. So what did we do? Let's summarize what we did. How do you write a net ionic equation for a precipitation reaction? Number one, you write balanced equation. Before canceling ions, we call that molecular equation because the spectator ions and real players are both in the picture. Next, write the ionic equation. That means anything which is water soluble breaks down to its counter ion. That means it breaks down to positive and negative ions. Next step, use the solubility rule. That means the table that you get on the exam. Use the solubility rule to decide which one of these formulas are not water soluble. And you call that precipitate and you write S on the right-hand side. That means solid. The rest of them are aqueous, water soluble. Then assume the chemical equation is algebraic equation. So cancel things which are not changing, and we call them spectator ions from both sides of the equation. And let's see this example. Silver nitrate, which is water soluble. Oops, no, not yet. Silver nitrate, which is water soluble, is reacting with table salt, which is water soluble. It makes a precipitate, which is silver chloride, is not water soluble based on the solubility rule, which I'm going to give it to you later on. And it makes sodium nitrate, which is water soluble. So if I were to do this, what is the first step? Should I break down the aqueous ones? So can I write, this is aqueous as well. So can I write this equation? See, AgNO3 is breaking to these two, right? Why is it breaking? Because it has AQ, water soluble. And ACl is water soluble, it breaks down to positive and negative as well. Then they are doing double replacement, and A plus is replacing AG, AG is replacing Na. That means AG is now partnered with Cl minus. This is what you get. And then you look at the table of solubility, you are going to say, you are going to see that AgCl is not water soluble, it's a solid. Sodium must replace Ag. So we are going to have NaNO3, which is water soluble.